my project supervisor is Dr. Surya Nurzaman, who is unfortunately unavailable today. Nevertheless, the show goes on. The structure of my presentation is as follows. It starts off with the introduction. Excuse me. He's recording. Yeah, we start off with the introduction and methodology, followed by the results and discussion, after which we follow the conclusion and references. Let's start off with the introduction in more detail. As you all know, we have wheeled and track vehicles, which are the most dominant form of transportation in the world today. I believe most of you who have got here today have used some form of wheel transportation. However, these wheeled vehicles are not able to access certain areas in the globe due to several obstacles such as large boulders, deep ravines, or steep slopes. On the other hand, we have natural-legged beings such as ourselves who can easily access these areas and move efficiently. As a result, artificial-legged robots are designed on these bases. So, these ordinary-legged robots, however, are too rigid because they have rigid structures and they have complex softwares along with powerful engines and transmissions, which sacrifice the cost, compliance, and energy efficiency. So these robots cannot really compete with their wheel counterparts. As a result, more compliant and energy efficient robots have been developed, such as the MIT Cheetah robot you can see below. This resembles an actual cheetah in terms of weight and size. It uses low weight, low power, high torque electric motors, which can be used for maximum energy efficiency. However, the robot cannot be used in certain terrains such as confined spaces. Now let's look at the C-shaped curve beam robot on your right. This robot exploits the resonance frequency and compliance of its elastic chassis in order to move. This robot is energy efficient, however, it cannot move at very high speeds. Now let's take a look at the overview and objectives of my project. A flexible mechanism is used by transferring one motion or force from one point of the body to another using elastic deformation. This is known as a compliant mechanism, which is employed in my robot. Also, the robot is actuated by a DC motor by inducing vibrations into its body in order for it to move forward. Also, certain objectives were set, which are to study the pattern of motion of this robot, along with changes in resonance frequency for varying shapes of the robot. Also, an investigation into the energy efficiency is done using a variable known as cost of transport, which is basically the power consumed by the robot divided by the weight times the velocity. This robot can be used in certain areas which are dangerous for humans or which they cannot easily access, such as places with radiation leaks or disaster zones. Now let's take a look at the methodology in more detail. First up, we have the design of the robot. As you can see on the right, we start off with the body. Body is made of a single beam which is bent into a U-shaped symmetrical curved beam. This curved beam rests on the feet of the robot, 2 feet, where each foot is made up of a single strip with rubber attached to its lower rear end. The actuation unit is made up of a DC motor with a rotating shaft arm and rotating mass. This shaft arm is rotated in an anti-clockwise manner in order to induce vibrations into the robot and allows it to move forward. Also, there is a shape-changing unit which has been utilized in order to vary the height of the robot so that it can move into confined spaces. Also, an accelerometer is attached to the top of the robot in order to act as a data logger to measure accelerometer readings in the X, Y, and Z directions. Now we see how the experimental setup is done. A power supply, as you can see on your left, is connected to a microcontroller and constant power is supplied, after which this microcontroller regulates the voltage supplied to the DC motor as well as the servo motors. This whole setup is placed on a wooden laminated table. Now we see the configurations of this robot. There are 3 main configurations used in this experiment. The first one on your left is the 20-degree configuration with a height of 10.8 centimeters, followed by the 30-degree configuration with a height of 12.4 centimeters, and the third and final configuration which is 40 degrees with a height of 13.6 centimeters. Now let's take a look at how the experiment was completed. One of the previously shown angles is set along with the required DC voltage, and the voltage ranges from 0.90 volts, which is when the robot starts to show some sort of locomotion, to about 2.2 volts, where the robot shows erratic behavior. So the CBR, also known as curb beam robot, is allowed to run a set distance of either 0.1 meters, 0.2 meters, or 0.3 meters, and the time taken, input voltages, and input currents are recorded. After which, the COT of the robot, which is the cost of transportation, can be calculated for each trial in order to determine energy efficiency using the equation shown, which is the input voltage times the input current times the time taken divided by the mass of the robot times the gravitational acceleration times the distance. This procedure is repeated 21 times for each voltage in the three configurations, after which mean and standard deviation of key variables such as input voltage, input current, power supplied, and COT are done. A plot of mean COT against mean input voltage is carried out. Also, the accelerometer is used to record raw data in the X, Y, and Z axes. The X-axis represents forward and backward motion in the sagittal plane. Y-axis represents sideways motion in the frontal plane, and Z-axis represents top and bottom motion in the axial plane. So this raw data collected is converted into time domain using a factor of 0.05986, after which it is converted into the frequency domain by a fast Fourier transform on MATLAB. From these results, a plot of maximum power coefficient against corresponding frequency value is produced. Now let's take a look at the results and discussion. First up, we have the method of locomotion. As you can see, two running cycles of the CBR is shown in the 30-degree configuration. The top row shows you a pattern of motion with the best COT, and the bottom row shows you a pattern of motion with the highest COT. Now what I'm going to do here is prove to you the equation of COT. As you can see here from the top right picture, the robot has moved a certain distance. Now let me tell you that the distance between each pink line is 0.1 meters. So the robot has traveled up to 0.3 meters in a time of 11.37 seconds. However, in the bottom right picture with the highest COT, the robot has only moved just a bit above 0.1 meters in the same given time. This shows that for a lower COT, higher velocity can be achieved, which proves the equation which states that COT is inversely proportional to velocity. Next up, we have the behavior of the robot, which is shown in a video. This shows that the robot can be used in confined space. The robot starts off in the 40-degree configuration, and it will in a moment drop down to 30-degree configuration in order to enter the tunnel with a constricted height. As you can see, the robot successfully enters the tunnel without any issues. Next, let's take a look at the analysis of the energy efficiency. On your right, you can see a plot of voltage versus COT. The three curves represent the three configurations. The black one represents the 20 degrees, blue one the 30 degrees, and the red one the 40 degrees. First, let's see the 20-degree configuration. The lowest COT here can be shown at 0.708 at 1.01 voltage, and the highest one can be seen at 1.51 at 2.17 volts. This curve shows an increasing trend upwards, similar to the 30-degree configuration curve, which is the blue one. This shows a low COT of 0.546 at 0.89 volts, which is actually the most optimum COT for this robot. Also, the highest COT for this case is 1.31 at 2.13 volts. Next up, we have the 40-degree configuration, which shows an inverted bell-shaped curve. The lowest COT here is 0.727 at 1.63 volts. As you can see, there is a slight increase and then there's a drop. This drop is seen at a COT of 0.772 at 2.04 volts. This may signify that the robot may have two resonance frequencies rather than just one, in the previous case shown. Also, the highest COT is at 1.49 at 0.94 volts. From all three graphs, we can see that the lowest COT is 0.546 and the other two are pretty close, which shows that overall the robot is energy efficient. Also, we take a look at the analysis for the fast Fourier transform. We have shown 3 plots for each configuration for the power coefficient versus the frequency. From all 3 graphs, we can see that the frequency in the x-axis, which is shown on your left, is higher than the frequency on the z-axis, which is shown on your right. Next, we can see that in the 20-degree and 30-degree configurations, the frequency in the x and z-axis have clear differences. This may signify that the robot moves in the sliding locomotion rather than in a hopping way. Next, in the rightmost one, we can see that they are almost equal. This may state that the robot shows both hopping and sliding locomotion. When we compare all 3 once again, we can say that all 3 graphs show that the efficiency in the 30-degree configuration is high because it has the maximum power coefficients. Some of the future works which have been proposed is a lighter and more compliant material should be used in order to reduce the COT of the robot. Also, I think it's best to 3D print the robot chassis in order to have the robot move in as one whole piece so that the vibrations can be induced accurately so there's no energy losses. Also, there were some limitations where there were detachment of parts and they were tangling, so I think it's best if the robot acts as one whole piece. Next, the robot should employ some sort of wireless technology and embed a portable power source in order for it to be accessed remotely, because one thing is to be used in the field, it should be portable, and another thing is that the wires always get detached due to the vibrations. Last thing, it should be investigated on different surfaces in order to know the different efficiencies. In conclusion, I would like to say economical curved beam robot designed to exploit the vibrational dynamics of its compliant structure was successfully made. Also, the shape changing ability and rotational frequency of the DC motor can be seen as the cost of transport is as low as 0.546, which shows that the robot is pretty efficient when compared to the MIT Cheetah, which has a COT of about 0.51. These qualities allow it to move in confined spaces with maximum efficiency. Also, the CBR can be used in certain tasks such as search and rescue, which need it to move in confined spaces. These are my references. I would like to thank Dr. Surya Nurzuman for guiding me throughout the way, even during the summer holidays, and I would like to thank Shiv and Gopi and Amit for helping me throughout this process. Thank you very much for listening to me.